In this video, we will talk about stars. To start, think about what stars you already know. You should know that the sun is a star, and we're going to talk about that today. Also, the North Star, also known as Polaris, is a star. That star is part of a larger grouping of stars called a constellation, and Polaris is in the constellation the Little Dipper, which is a part of an even larger constellation called Ursa Minor. Most stars are made of hydrogen and helium, and these are the two most abundant elements that we find out in the solar system, so it makes sense that we would find these elements in most of our stars. All stars are going to get their energy from nuclear fusion inside the core of these stars. So that means our sun also gets its energy from the process of nuclear fusion. To fuse something together means to bring two things together. So if we look here, we first start with hydrogen. We're going to put those hydrogen atoms together, and what we come up with as the product is helium, because we have one proton and one proton coming together to two protons, making helium. And as a result, energy is also something that we end up with, okay? And this is what's going on inside of our sun, which provides us with this energy. And like we said earlier, stars can be grouped into constellations, and here's just a small map of some major constellations. We're going to touch more on this later on in the unit. Stars can differ in mass, size, and surface temperature. Their surface temperature affects the color of the star. So if you look at page 15 of your reference table, you can see at the bottom of page 15 of our reference table that color is across the bottom and surface temperature is right above there. It's a little bit backwards on this chart. Our cooler temperatures are on the right-hand side, while our hotter temperatures are on the left-hand side. If we see here, red corresponds to the cooler colors, 3,000 to 2,000 Kelvin, whereas blue corresponds to the hotter colors, 30,000 to 20,000 Kelvin. So what you would like to do if we ever ask you what color a specific star is, all you have to do is find the star, go down, its temperature is there, but also you can just keep going further and its color will be there. So just remember, red represents our cooler stars, blue represents our hotter stars. Page 15 of the reference table also talks about the luminosity of a star. Luminosity is your total energy output of a star, so really we're talking about how bright that star actually is. Luminosity will depend on size, and it also will depend on temperature. But if you compared two things that were the same temperature and one was bigger, the bigger one would be brighter. Okay, so the bigger something is, the brighter it usually is as well. So let's take a look at page 15 of the reference table. Now we want to look at the left-hand side here. You can see luminosity. And what's interesting about this chart is that we're comparing everything relative to the sun. So if we find the sun here on the chart, it is a 1, and everything else is compared to it. That makes sense because the sun is the closest star to us, so it's obviously going to appear brightest to us, although compared to supergiants and giants, those are definitely more brighter than our sun, which is a main sequence star. So if we look here, the sun, Alpha Centauri, all of these stars are within the main sequence. White dwarfs here like Procyon b, that is going to be hotter because it's white in color, but definitely lower in luminosity, so more dim. Giants, up here in this section, they are going to have a higher luminosity than our main sequence stars. And supergiants are going to have the highest luminosity on this chart. Okay, so Betelgeuse itself is a great example of what we were talking about earlier. If we compare Betelgeuse to our sun, Betelgeuse, if we look at our temperature, is in the red section. Our sun is in this yellow section. So Betelgeuse is actually cooler than the sun, but it's a lot bigger. It's a supergiant, which makes it a lot brighter. Its luminosity is higher. So in review, we want to put this into our notes about the different colors of stars. Remember on page 15 of our reference table, what color is a hot star? You want to fill in there. Hopefully you remember that that is a blue star. And then what color is a cold star? That would be the red color. Okay, and again, you don't really have to memorize that. It's right off your reference table. So today we want to talk about the life cycle of a star. When we talk about the life cycle, we want to look at the Hertzsprung-Russell diagram, or the HR diagram, that plots a star's luminosity against its surface temperature. That is page 15 of our reference table. So what we were just looking at, and what you should still be looking at, that's the HR diagram, okay? The diagram also talks about not only temperature and luminosity, but it shows the life cycle stages of a star. Most stars are in the main sequence, and if you remember, if you're looking at your reference table right now, you should be able to find that our sun is part of that main sequence, and underneath the term main sequence, you should see the words early stage. If you look at giants and supergiants, they're in the intermediate stage, and white dwarfs are in the late stage. So we're going to go through the life cycle here together, and please make sure you're looking at your reference table at the same time we're doing this. So the different types of stars here, let's first start with the giants. Giant stars have a diameter 10 to 100 times greater than our sun. Remember, that makes them bigger, so they're brighter, so they're more luminous. Main sequence, where our sun is, are actively fusing hydrogen and helium. About 90% of stars are this type, and our sun is one of them. Supergiants have a diameter more than 100 times that of the sun. They're very luminous, but they tend to be cool. And white dwarfs are stars near the end of their lives. So if you look at your reference table, you will see that under the word white dwarf, you'll see late stage. How are stars born? Okay, just like humans go through cycles throughout their life, you know, you're an infant to a teenager to middle age to someone who is elderly and near the end of their life. A star does the same thing, obviously over a much larger span of time though. All stars are going to be born the same way. They start off as a nebula, which means it's just an area that consists mostly of gas and dust. That area will begin to condense upon itself, and remember, when things get closer together, the temperature is going to increase. As the temperature increases, parts may start to glow, which is called a protostar. And we really technically do not have a star until that fusion begins. Remember, nuclear fusion in the core, that's how stars get their energy. So unless we have an energy source, a star technically is not born. So we know how they are born. How are they going to die? Well, once a star is born, it's either going to be a star like our sun, which is known as an average star, or it's going to be a massive star. Okay, so we're going to talk about both separately, but let's talk about a star like our sun. A star like our sun, after its main sequence stage, will swell to a red giant stage. And the reason it's going to swell is because instead of fusing hydrogen into helium, now it's going to fuse helium into much heavier elements like carbon and oxygen. Okay, so it's going to swell up to red giant stage. Eventually, as it gets to red giant stage, some of those gases at the surface will blow away, and when all the gases at the surface are blown away, only the core is left, which is called the white dwarf stage. So eventually, our sun, its final stage, will be a white dwarf. A massive star is a little bit different. That's going to keep fusing until it gets iron and nickel forming. Once that happens, that's going to swell really big to a supergiant stage. After supergiant stage, we have observed that supernovas occur. Supernovas are like an explosion where your core in the star is collapsing. This explosion is about like 1,000,000 times brighter than the original star's brightness. So it's a really giant explosion out there in space. The end of a massive star's life can either become a neutron star, which is just that core that's left, or it could become a black hole. And a black hole is an area where the gravitational field is just so intense that not even light can escape it. Okay, so here's just some pictures showing you what this might look like. So remember, the life cycle, really the fate of the star depends upon its mass. Is it a massive star, or is it a star like our sun, an average star? So remember, a star like our sun will end up being a white dwarf. A massive star will either be a neutron star or a black hole. So I want you to pause the video and fill in what you see here on your diagram. Remember, the beginning stage is nebula, huge ball of gas and dust. If the star forms and it's an average star like our sun, it will swell to red giant stage, and then when the gases are being blown away, we're at planetary nebula, and eventually when they're all gone, final stage is a white dwarf. If it's a massive star, it will swell to red supergiant. If the core collapses, then you're at supernova stage, and then their final stage, if the core is just left, it's a neutron star, or potentially it could be a black hole. So this is the life cycle of our stars, and we can really look at our reference table to kind of help guide us. So let's just take one quick glance at that one last time. We can see here that early stage of life is our main sequence stars. Then our intermediate stage would be our giant or a supergiant. Remember, our sun will go to giant stage. It will never be a supergiant. Only massive stars will be supergiant. And then eventually late stage is white dwarf. A star like our sun will eventually be a white dwarf, but if it is a supergiant, it will end up being a black hole or a neutron star. Okay, so anytime you're asked any questions about the stars, you want to go to this HR diagram on page 15 of your reference table. You want to remember that the color and the temperature kind of go together, and luminosity talks about the brightness of a star compared to our sun.